It's like this is not. Yeah, of course. I will, in a few minutes, I will start.
And Nikki, nice to meet you finally. And this is Nathan.
Hey, sorry.
Don't worry, we're going to start in a few minutes. Have a seat.
Get some food.
No more food, but drinks. Yes.
Yeah, we had an order. Yeah, right there.
I'm not afraid of bringing kids up to like, hey, these are real serious issues. You should know about it. Most parents would tell us our kids.
Nice to meet you.
About helping.
Lisa will go into introduction again.
Yeah, I'm all over the world, you know.
Then we cannot.
Let's switch to yours.
Mine is not working.
Let me hold it. You want to try to restart your camera? Oh, sorry.
I don't know. Let me get rid of this.
Try to restart your house.
I said, nice to meet you.
Yeah. Some other
Some other. Did you try to restart your camera?
Yeah. That's what I did.
What's the pronunciation?
He's got to be up there. I think he's got to be near here. He can't be in the back. Get him up there.
Yeah. Every meeting is like proud. We got to show my house. Yeah, you got to think that's their own computer. Everything's on their computer. You know, it works there. You switch computers, might be.
What? Are you ready? I don't know. Later, when we start.
Go out to the lobby and ask them.
What time is it now, Nikki? Is it 6?
Yeah, almost.
What's almost?
Almost 6. Is this recording alive?
You can, I think you can download it.
Oh, you can download it. And now we can hear us?
They can hear me.
Okay.
Oh, let's sit down. Nice to meet you.
Hey, I'm Isaac.
Yeah, nice to meet you.
You can keep it.
I can.
Yeah.
Anyway,
It's not working. Sorry.
That's fine. Don't worry. We have this one.
and he wants to come up and say something, and going to make up and up and say something. And we'll stumble into it. That's it. That's how it's done, right? Henry.
I just.
Yeah. Okay, I'm ready.
No, you're not ready.
I'll stay put. I'll stay
I'll
put.
give you the clue.
I'll be quiet.
I'll give you the clue.
Get started. This is my
I don't know. I'll leave that.
Get the, if you need help, get their desk, get their IT guy.
I'm going to move it a little bit because it's my back. And when it starts, so the I can tell it's still in my. It is. Is that okay if I move it? Move it to the middle? Is that okay? I put the
I think it's okay. Sideways.
it's the computer is right in the.
Who's sitting here?
Nikki is sitting behind
Do you know how to access Wi-Fi?
Oh yeah. Charger password is on mine. It's a where is the Wi-Fi? Do you know the one?
Come say hi.
I did, but I couldn't find the Wi-Fi. Sorry. Do you have that Wi-Fi? I tried it, it doesn't work. There's no
I'll be right over there. Yeah, I got
It's not? No. So I think that's the lab. Maybe it's. There is no.
Rob.
No, there is no power to the cable. The cable is under, just wrapped around.
Good evening. Hello, everyone.
So my guess is.
It's great to have all of you here tonight. Grab a seat if you can. Good evening. China is investing $10 billion to build the world's largest quantum research facility. The quantum race is very much on. However, there are less than 1,000 people in the entire world is engaged in the quantum research. There's a serious talent shortage. When self-driving truck displays 3 million jobs in the next few years, we need to put all of them to quantum computing work and some more. I'd like to give a little background on how we gave birth to this event. Let me see if Henry is around. Henry, are you here? Okay. Henry is the CSPA chairman of the board. He came to me a few months ago. He told me that the blockchain and artificial intelligence are so last year. It is time for quantum supremacy. So we went out, tried to collaborate with IBM on a quantum event. Being IBM, they move at IBM speed. So nothing materialized for a few months. And then at a random barbecue event in Palo Alto, we met Isaac Kim. I think it is pretty quantum entanglement or superposition or both. This event is made possible by the generosity of so many generous sponsors and volunteers. First, let me introduce my associate, Nathan. Nathan coaches startups on sales and marketing strategies. I don't know anybody who is more thirsty for knowledge than Nathan. In the last few months, he has bought and read more quantum computer books than Stanford has. By the way, tomorrow at this very place, same place, there's an all-day conference by the VC task force on finding your first investor.
Should we start?
Yeah.
Slides, okay. Hi.
I will let Nathan start
Hi.
to share one secret to Silicon Valley.
I wonder if we can get somebody to ask the people on the lobby if we can get some microphones in here. We need microphones for the speakers. Can you ask them? Somebody ask them, please. Okay, so we wanted to, an event like this wouldn't be possible if we didn't help from certain people making it to pull this event off. So that's I wanted to talk for a minute about the secret of what makes Silicon. Let's just take 30 seconds. What makes Silicon Valley such a special place? Okay, and okay, so it's a meritocracy fueled by reciprocity. That's one way of putting it. I think that really represents what's different here than most places. So the reciprocity part is what I wanted to talk about. There's a few organizations and people that helped us put this event up. So I just wanted to mention them very quickly. So if you're in need of their services, it's appropriate that you give them some consideration, okay? And one is tomorrow here, there's going to be an event here at this DLA Piper. They're going to speak in a few minutes. They'll tell you about themselves. But it's really great that they offer us this hall, and this enables us to have these events. We don't have to charge for them. So there's an event here also tomorrow for startups by VC Task Force. That's somebody we collaborate with. So it's here all day today. Okay, so let me go over some of these people. There's Piper we talked about. Deutsche Bank, are they here? You guys want to say a few things here? So if it wasn't for them, we wouldn't have the food. That's kind of nice, right? The food and the wine.
Did everybody get a slice of pizza?
Yeah, so
So I'm just going to speak for one quick moment, but when you're done, you're going to have to determine which one of us has a PhD in mechanical engineering. So at least we can participate in the conversation a little bit. Just quickly, Deutsche Bank really appreciates Henry and the generosity of CSPA to invite us to come and meet you. I'm a private banker in the wealth management group at Deutsche Bank in San Francisco. Really, the goal here is to let you know what we're doing. We help entrepreneurs and founders and venture capital firms invest our money, find ways to invest our money. If there's anything that we can do for any of you that are in the room, I imagine as you come up with your next big idea, there's probably a lot of planning and a lot of work that needs to go into what you're doing on the personal side. So obviously, if there's anything that I can do to help, please don't hesitate to reach out. We are, as a platform, always looking for good investments for our clients. So we do onboard select direct investments. So quantum computing, CRM, software as a service. We're raising money for a big rideshare company right now, one that you might not know about. And if there's anything that I can be helpful with, please. We're a big global investment bank. If there's anything that I can be of service, my name's Jake Block. Henry has my contact. If you'd like, please reach out. So with that, before I kick it off for the rest of it, who thinks he has a PhD in mechanical engineering? Raise your hand. Who thinks that I have a PhD in mechanical engineering?
And who thinks neither of us have a PhD in
All right, well, he wins. So if you have any questions about tonight's topic in a layman's standpoint, how it affects banking, please ask Michael.
Nice to meet you guys. Enjoy.
So next we have, we told you about this as an event here tomorrow for startups, okay? Founder Space is someplace I'm a mentor. If you're into startups, people that are doing startups, they have facilities all over the world. You can come and see me or look them up. And they have an event tomorrow. So if you want to know about it, it's a good place. If you're fairly new to Silicon Valley, you go to one of their events, you get good immersion there. Or you can ask me about it later. They have an event tomorrow. And also ZGC Capital. ZGC is the footprint of the Beijing municipal government in Silicon Valley. So if you're doing things in China, there are people that you should know about. They're in Santa Clara. Startup Digest, some of you might be here because you heard about us from Startup Digest. They're the original announcement list. They curate announcements and they send them out. They're sectioned off by different regions all over the world. So if you want to know what's going on in a particular region, that's one good place to find it, okay? And this is me. This is my meetup that I do where I take really recent discoveries from neuroscience and I apply them to marketing and persuasion and sales. So, and also we have here one of our speakers, you'll talk about in a minute, Will is having an event in 2 weeks here in Silicon Valley. You'll hear about that more, Quantum for Computing. And also one of the books, Terry Rudolph is here, one of our speakers, and this is just a book he published. And if you wanted to get one book for quantum, learn about quantum computing, and if you're just new to the field like I am, this is a pretty good start. It's only 150 pages, and it just came out, right? Okay, and it's well worth it. It's an easy read, and it's very inexpensive too. Okay, so without further ado, we'll get started. We're going to turn this over to Dr. Isaac Kim, who's going to moderate this. But before we do, just to give us a sense of who we are here, and also to help out the panel, I was hoping we could get a show of hands. Maybe we can divide the audience sort of into maybe two groups, perhaps three. One is, how many people here are professional physicists or professional STEM, have a professional STEM degree that understand quantum computing and quantum mechanics, right? That's interesting. So what would you say? That's about, I'd say 20%?
20-30%.
20-30%, okay. So I imagine, but raise your hand anyway, does that mean the other 70% are just people like myself who are informed, just have a general background and want to know what's going on in the field, right? Is that the rest of us? That's about 30-40%. Where's are we in a superposition here? And there you got it. The rest came for pizza, right? That's okay. That's good, right? All right. I think that's a good enough start. All right.
Let me just say a few words.
Oh, sure.
About. So Dr. Isaac Kim does not need an introduction in the quantum computing community. He got his BS in math and physics from MIT, PhD from Caltech. Now he's a postdoctoral scientist at Stanford. I avoided all three schools, so I didn't have to deal with the rejections. It is because of Dr. Isaac, we're able to assemble a star panel tonight. It is with great honor and pleasure, let's welcome Isaac. And he'll lead this evening's discussion.
I'm gonna almost blush. Thank you. Yes. So thank you all for coming here. Clearly we have an overflowed room. So let me just tell you about today's plan. So we will have roughly 1 hour allotted to these speakers telling about what they're doing right now. And I will give you max 10 minutes for each firm. And this will be If you don't want to use up to 10 minutes, that's fine, but please don't go over it. And after that, we will have a panel discussion followed by a 15 minutes of a Q&A session. So if you look at the schedule, it says that there's like a 1 hour panel discussion. I want to allocate the last 15 minutes to the questions that you might have. So if you have any questions while these guys are talking, save it for the last minute. Okay, so before we begin, let me just introduce everyone. So here we have Terry Rudolph from PsiQuantum, and we have Matt Johnson from QCware, Brian Carl from Rigetti, and Stefan Leichenauer from X. He's a visiting faculty at X, and we have Prithik Pusma from Cambridge Quantum Computing. So who's starting?
It doesn't matter. You want to go this way, or do you want to?
Whatever is more
Okay,
convenient.
you want to go first? Sure. Okay. Help you plug in here.
Yeah, I can just use this.
Goes right here. You're up. Very good.
Can I see it?
Yeah.
Do I need to check them up there?
Unless you can, yeah, maybe you could. Will that fit? Let's move this over here. Will that come over here? I think that'll move. This thing will move.
That cable will not stretch.
Yeah. Well, yeah, it might. Come on, it will. It will. Yes. I'll meet you on that. You in? There we go.
Yeah.
All right.
Can you guys hear me? Yeah. So hi
Topic
everyone,
is
my
very-
name is Krithik. I'm from Cambridge Quantum Computing. Thanks for having me, and for all of you, thanks for attending today. I hope I can share some things about quantum computing and CQC. I'll keep it pretty short. Yeah, I'll just keep it to a few slides if that's okay with you guys. So CQC is a quantum software company. We're from the Cambridge, UK. Most of our scientific team is from the UK, but we have offices now in London, now in Berkeley, which is where I'm based out from, DC and in Hong Kong. And most of the employees that we have are all scientists, and we have a few engineers as well. And most of the business development and the business side of the people are in the US. And so the kind of the core focus areas of our company is, and again, it's mostly all quantum software, but we do quantum machine learning, quantum chemistry, quantum encryption, and our hardware device, which we've recently been developing, is all in encryption. And then finally, what we're probably well known for is our operating system and our compiler, quantum compiler. And I can go into a little bit of detail for each of those subsections. So some of the recent developments we've had in quantum machine learning, I'm not going to give a primer to quantum computing. I hope that's okay. I will probably cover a little bit of that in the discussion. This is just kind of giving our company overview. But some of our developments in quantum machine learning are in generative learning, which is something that's a little tricky in classical machine learning. And so we have some algorithms we've developed by our scientists in Cambridge. Adversarial quantum circuit learning, which is useful for pattern recognition in AI. And finally, we've been developing some rudimentary algorithms in if you're familiar with bars and stripes, that's an application we've been using in pattern recognition. So these are kind of the projects we've been working in machine learning and quantum machine learning. Finally, quantum chemistry. We recently had a partnership with JSR, Japanese Synthetic Rubbers, and we've worked on a very successful chemistry project with them. And are there any chemists in the audience or quantum chemists at all? No one? Kind of. So we were able to calculate multi-reference states. I don't know if you're familiar with that, but it's the first step to calculate excited state properties in materials. And this is useful because one of the biggest applications in quantum computing is to simulate nature and use these machines to accurately predict properties of things that we can't do using classical computers or are intractable in classical computer simulations. So that's a subsection of CQC as well. We've also been working on quantum encryption. I recently actually just came from an event where we were discussing a lot of encryption software and post-quantum cryptography, and this is a big area, and I think one of the key areas that people are most concerned about with regards to quantum computing. And this is where we're not a quantum software company, but we're developing a physical hardware device called Iron Bridge. Yeah.
Do you have a quantum key management system?
A key management system? No, we don't have a key management system, but we have this device which assists in distributing keys. So it's not a management system, but close to it. This device also has quantum random number generation, which is super useful in algorithms for quantum cryptography. And it's self-certifiable, something that really no other quantum cryptography company has been doing, the self-certifiability. Finally, our operating system, which again, what I said, we're probably most well known for, and it's called Ticket, which the T stands for our CTO Takis and Ket from physics, and it's our quantum compiler. We often get questions about what is a quantum compiler, so I can kind of give you an overview of that. But essentially, when you're doing higher level programming, and when you have the basic language that if someone in the future we're going to write, you need to break it down into the quantum circuits. And so each machine, for example, whether you're using IBM or Google, has their own topological constraints, the constraints with the qubits. And so this compiler takes into consideration all of this. So it seamlessly integrates your programming language in the higher level and programs it down to the circuit level. And so this is very useful for when you're having, again, different types of qubit architectures, which I think we'll also go over in this panel probably. And so these are some of the partners where we've given our compiler to, such as IBM and Google, and some of the British powerhouses such as NKIT and Oxford Quantum Circuits. And so that's all I really have. I thought I'd make it pretty short. And so if you guys have any questions, I can probably field that now with regards to CQC. Go ahead.
So from a business
Could you stand up if you ask your questions so everyone can hear it, please? Thank you.
From a business perspective, how are you dealing with the fact that the current quantum hardware available is on the small side?
Yeah, sure. So our main focus right now is actually in the quantum cryptography kind of subsection of our company. We've been selling Iron Bridge and are in the process of kind of developing that. But the idea is that we're going to wait as the hardware improves over the next few years. We're going to be developing the quantum software on the side. Mm-hmm.
Simulating nature, can you elaborate that on whether it's a global scale or more like human independent scale?
Sure. So right now, classically, we can simulate molecules or atoms. There's standard theories which we can use in computational chemistry. And usually you employ supercomputers to do this if you're going to calculate. For example, in my research, I did magnetic materials, and you needed a lattice structure of magnets, and you want to calculate how does it respond to light or something, right? So you need supercomputers to do this. And so it gets difficult when you have really large systems because you have to account for nearest neighbor and the nearest neighbors. And so it becomes intractable very quickly. And so the idea is that in quantum computers, when you can kind of simulate this, assign chemistry to the qubits, manipulate that problem into a quantum computing problem. It becomes a natural way to compute these molecules. So I kind of answer that question.
Thank you.
Yeah.
I think we'll have to move on to the next speaker. Sorry, but you'll have another chance towards the very end.
Okay.
And let's first thank Kritik for. By the way, we will also have time after the Q&A session. So if you want to come up after that and ask these guys, that'll be also good. So we have Stefan, and he will tell us about his recent efforts on quantum computing.
All right, great, thanks. So I don't have slides. I'm just going to talk for a few minutes. As Isaac said, you know, I am the visiting faculty at X. And you know, the emphasis there, I guess, is on the visiting. I just want to, you know, say that I'm not like a real like Google employee, and I'm not here representing Google or X or Alphabet. I'm just going to tell you some of my personal opinions about quantum computing, and these are the same things that, you know, I tell people at X. You know, because the reason why they have me there as visiting faculty is because they value some of the things that I say. So I'll tell you, I'm gonna play a little bit. I think I'm gonna put myself in the role of the wet blanket. Okay, I'm going to try and fight the hype for quantum computing, and the rest of the panel can use me as a foil if they want. But I'm going to say a little bit about what I think we can do now versus what we would like to do, and maybe what we can't do probably for another 10 years or so. And I'll also say that I'm a scientist. I'm not a business person. I'm not an entrepreneur. So I may be in this crowd. I'm a little bit of a black sheep. But okay, that's the introduction.
We'll forgive you.
So, I mean, since quantum computing is really awesome, no one's going to argue with that. Since the mid-90s, we've known about, you know, these really crazy things like efficiently factoring numbers, which can, you know, break encryption and all that, or this, you know, modern encryption and stuff. But, you know, as was already brought up in one of the questions, quantum computers that exist now and will exist probably for the next 10 years are too small and too error prone to actually do those really awesome things. Okay, so if you're intent on using quantum computers to factor numbers, for example, or do you know, factoring numbers is the classic one, but even something as really interesting as really simulating a molecule for quantum chemistry or protein folding or something like that, that's still probably at least 5 years out. Okay, but what can we do now? What is the you know, that's I guess the bad news, but I think that's the right perspective to have. What is quantum computing good for now? Why am I interested in it right now? And why I think why are these people on the panel, you know, spending their lives in quantum computing now, rather than 10 years from now? And there are a lot of interesting sort of things we can possibly do. We just have to, you know, be clear about what those are. So what a quantum computer does, you know, for those of you who don't know, a quantum computer, you give it a recipe. Say, I'll use the sort of universal quantum computer model with quantum circuits. You give it a quantum circuit, which is a set of instructions for it to perform. And then you measure the result. And it's going to output some string of zeros and ones. Okay? As the number of zeros and ones you get are the number of qubits in the system. And it's going to output those randomly. Every time you run the circuit, you'll get a different answer. But the distribution, probabilistically speaking, is going to be skewed in one way or another, or different kinds of strings, different kinds of bit strings, strings of zeros and ones. And what we can do, okay, the reason why quantum computers are neat is because we can very carefully engineer this recipe, this set of instructions, such that the probability of getting one sequence of zeros and ones versus another is skewed in some direction or another. And the problem that we have, you know, to face is, can we come up with interesting interesting recipes, interesting sets of instructions to give to the quantum computer, such that the output that it gives us is skewed in a way that solves some interesting problem. And there are plenty of problems that are of this type, okay? Like if you want, you know, just to speak in like a little bit of a mathematical language, if you want to find the if you want to find the input to a function for which that function has the smallest value of all possible inputs, but you don't care if you get actually the smallest one, you're okay with an approximate answer. There are quantum ideas for solving this kind of problem using a noisy near-term quantum computer. It's not as exciting as factoring, but it's something that we might be able to do. And the kinds of questions we should be investigating and answering in the near future is which kinds of problems can we phrase in this way? And which kinds of problems can we phrase in this way, and which of those problems can a quantum computer actually solve more efficiently than a classical computer? Okay? And this sounds boring compared to factoring, but it's still potentially really cool. The problem is that we don't know the answers to those questions. We don't really know which kinds of functions the quantum computer will be good at minimizing. We don't know really which kinds of real-world problems that people care about can be phrased in this language, which then can then be put on the quantum computer. And that's, I think, what a lot of the work is going to be in this near term, in this next five-year period. It's going to be really fine-tuning those recipes, those sets of instructions you give to the computer so that it can solve this kind of problem more easily. And also winnowing down the list of problems that can be phrased in this way. Okay? That's one thing. Another thing that I think is important to think about right now is quantum computers are very complicated, right? I mean, most people I know who work on quantum computing have PhDs in physics or computer science or something like that. It's, you know, there's a very high bar. Most people who work on regular computers, you know, who are software engineers, don't have PhDs in computer science, but they do just fine. Okay, there's a bit of a gap, right? Sort of an education gap, and that's something that we can start solving today. 10 years from now, when the quantum computers are big and powerful, we're going to need a quantum software engineer workforce to run them, okay, to program them, to figure out what the good quantum algorithms are beyond just the few that we've had since the 90s. And that kind of workforce training is, I think, something that is going to be a big deal going into the near future. You know, taking a physics course in a physics department on quantum mechanics is not so great for getting the right kind of quantum mechanics background you need for quantum computing. There's a sort of a specific set of skills that, you know, people pick up slowly over time as they move toward a PhD and beyond. But you could condense all that and, you know, really give that kind of quantum workforce, you know, the education system can catch up. So I think, well, I hope I've given you an idea of maybe what we should really, you know, set the expectations a little bit for what we should be thinking about for the next 5 years sort of term, and not get too caught up in the really cool sounding applications. But it's going to be, you know, I'm a scientist, and this is really a good science problem. It's an era of discovery where we have to try things out, see what works, and iterate slowly to make progress.
I guess we have 1 minute for a question.
Very interesting. What do you think the intersection is between deep learning and quantum computing?
Could you repeat his question?
Yeah. So the question was, what's the intersection between deep learning and quantum computing? I think there are many intersections. So besides the fact that they're both, you know, topical. So there's a similarity there, where in deep learning is another kind of subject where you don't really know beforehand what's going to work until you try it. Okay, and over the last 10 years or whatever, the computers have gotten the GPUs and whatnot have gotten powerful enough that people can try really interesting things and have made good progress. And the same thing, I think, is about to happen in quantum computing. Okay, the progress won't be as rapid because quantum computers are harder to build. So the GPUs can get better much faster than the quantum processors will get better. So that's a parallel, I think, and I think the history will look back and say that the evolution of quantum computing is going to echo deep learning. But the other comment is these two things can work well together, and I'll just give a heuristic point of view about why that might be true. So part of what deep learning is good at is the problems which are solved by deep learning are the classical computer through deep learning can become superhumanly good at doing certain tasks. Okay, there's famous examples of playing chess or Go and whatnot. Programming a quantum computer is really hard. Okay, in fact, programming a quantum computer is so hard that you would not expect even a super smart AI to be perfectly good at it. However, if a super smart AI through deep learning is even just marginally better than a human is at programming a quantum computer, well, that's good. And so I think using the methods of deep learning applied to generate new quantum algorithms, for example, is, I know a lot of people are interested in thinking about those kinds of things.
Let's thank Stefan again.
Okay, this one might, you need HDMI to put here. Yeah, that'll work.
Thank you. Thanks for that.
Right.
Yeah, I know, technical difficulties, man. Let's see.
Okay,
Okay, it works.
So we have Ryan Carl from Rigetti Computing.
Hi everyone, my name is Ryan. I'm a product manager at Rigetti Computing. I'll talk a little bit about Rigetti. Happy to answer any questions now and after this panel. So a little bit about Rigetti. We're the first full stack quantum computing company, and so I'll get into a little bit about what that means in just a second. So we have about 100 employees. We've raised about $120 million to date. We're based in Berkeley, California, and we also have the only fully integrated fab facility for quantum integrated circuits in Fremont. So fun animation to talk a little bit about what a full stack quantum computing company means. So it means that we actually design and fabricate our own chips in our Fremont facility, and we actually operate these chips in our control systems, and then we offer them through a cloud access point, which we call Quantum Cloud Services. We also offer abstractions away from a quantum computer, at the first level being a Python-based instruction set architecture for our quantum computers. And we also offer Grove, which is a toolkit for building quantum algorithms. So this is what one of our quantum computers look like. There's I guess Terry will talk a little bit about what PsiQuantum is working on. There's a few different ways you can build a quantum computer. We're building a quantum computer based on superconducting qubits. So we use typical, or I guess traditional nanofabrication techniques, and the only differences are operating conditions are much colder. So our chips operate at a temperature of about 10 millikelvin. So if you see the bottom of that picture on the left, that's where the chips sit. There's a big shield that goes over it, and then it gets sealed up in this big thermos-looking thing, which we call a dilution refrigerator. And this is our fabrication facility, or at least a part of our fabrication facility in Fremont, California, where we actually fabricate the chips that we design. That's what a wafer looks like. So that contains 8 actual chips. The chips are a little bit smaller than the size of your pinky nail, so you actually can see the qubits on them. They're macroscopic.
And that's an 8-qubit system. So you can see the 8 squares around each of those. So we've just announced our new flagship product, Quantum Cloud Services, which is a cloud access point to our quantum computers. We've had quantum computers available that you can run on over the internet for a little over a year now. And now we're offering a much more HPC type access point to our quantum computers. So another fun animation of kind of what that looks like. We offer an access point that is effectively similar, like I said before, to an HPC access point. And we've built in a bunch of fun resources that I can talk about when I have more time later. So also, I threw this slide in for the folks in the room who are interested in doing business development. We have announced a Quantum Advantage Prize, which is a $1 million prize given to anyone who can use a quantum computer to demonstrate what we call quantum advantage. So you'll hear terms like quantum advantage and quantum supremacy thrown around a little bit. Quantum advantage is the point at which you can use a quantum computer to solve a problem better, by giving a better solution or better approximation to the solution faster or cheaper than you would spend on an HPC type resource. So that's it. And with that, I'm happy to take any questions.
So I applied for your beta access a while ago, right? Haven't heard anything. Is there a fast track?
Yeah, so you and Isaac and probably a bunch of other people in the room have been waiting for beta access, and we're sorry for the delay. Effectively, we have put out an entirely new, so that Quantum Cloud Services platform that I announced is effectively an entirely new product. So we had a web API access point to our quantum computers, and so you would expect if you were going to run a program on a quantum computer, it would take about 3 or 4 seconds for that program to go from your laptop over the public internet to be compiled and executed on our quantum computers. So with this new kind of HPC type access model, which we call Quantum Cloud Services, we expect that to be executed on the order of milliseconds. So it's been a lot of engineering over the past 6 months, and so we're actually really proud to announce that we're just moving out of beta access after last week with our first 16-qubit processor. Isaac actually will be one of the first people who will be testing this platform. So with that said, if there are a lot of people on our waitlist, we have had thousands of people get onto our waitlist. So put up my email before I can talk to you after too, but if you're interested in getting up a little bit, you should reach out to me.
Well, what's the most advanced unlimited advantage computing you have achieved so far?
Oh, we haven't achieved quantum advantage. I think, like Stefan said, I think quantum advantage is something that we expect to be at least a couple years away. It requires a really robust and powerful quantum computing resource.
What kind of application will you achieve first?
Oh, I think we're going to get into that in the panel, but I think there's anything, it's a powerful resource for solving really hard problems. So you can expect that maybe it's interesting for combinatorial optimization problems or anything to simulating other quantum mechanical systems.
I think the question is, do you want to expect better first, faster first?
Oh,
Could you repeat his question?
yeah, okay, so the question was, when we talked about advantage, we said better, faster, or cheaper. My expectation is it will probably be, we'll expect better first. There are some problems in condensed matter physics that we think we can give better solutions to. There are certain, for our chemists in the room, there are certain variational algorithms you can run on our platform that give you a unitary coupled cluster level approximation of an electronic structure.
Since you're a fabrication company, can you speak of the equivalent of Moore's law, where improvement in hardware can drive the scaling of performance of quantum computing?
Yeah, so I think we'll hit that at some point. Oh, sorry about that. Yeah, so the question was, is there a Moore's law equivalent that we'll see with quantum computers? I think there's probably two. I think the first threshold is the one that's most proximate, which is this chasm between kind of these noisy quantum computers that are very small in scale that we have currently, moving to large fault-tolerant systems that are going to be able to solve really hard problems like the perennial Shor's algorithm and stuff like that. And then, after that, you'll see probably some Moore's law type scaling.
Last question.
So when you were talking about You use the word commercial. Does that mean you're selling out bad services?
No.
Not really.
Not yet. Maybe one day, but no, not yet. Cool. Thank you.
Okay, let's thank Ryan again.
Still attached. Thanks, man.
Okay, so we have Matt Johnson from QCware.
Excellent. So thanks very much to the organizers for inviting QCware to participate today. And on a very personal note, I think it's really satisfying to talk to crowds like this, because I think if you look at like the very broad demographic that's here, it's probably very similar to the types of crowds that show up every time a new emerging technology makes its way into the valley. And you know, I think really if you look at these grainy kind of footage from the 70s of the Homebrew Compute Club, or, you know, and you look at like the audience, it's kind of very similar. So, and I also think it's quite relaxed, because I and I think the other panelists, we don't really have an agenda here tonight except for kind of transmitting some information. And I think most people here don't have an agenda other than kind of learning something that they hope is a little bit interesting. So I'll spend just a couple of minutes talking about our company, but also about the context of quantum computing, or quantum computing as we see it at a very practical level, because those two things are kind of intertwined. So my name is Matt Johnson. I'm the CEO of QCware, and we're a quantum computing software company based in Palo Alto and about to open an office in Paris. And very simply what we do is we're trying to do for quantum computing what Oracle did for relational database management. So they kind of took this very hard to use resource and put it into the hands of users that are more easily able to access this resource. So in our case, when we think about the eventual adoption into the enterprise community of quantum computing, we think the first adopters are going to be basically everyone with a GitHub account. People that are working in high-level languages and want to consider this resource as an accelerator, like a GPU or an FPGA, an ASIC, something like that. Something that for certain problems, this particular resource will help them get a quicker time to solution. So really just like more speed. So just to put the way we look at quantum computing in context, if you think about that dark blue outer circle, that's kind of the universe of problems that can be solved with all the classical computing resources out there. Just make up a type of resource. Within that, there is a class of problems that can be expressed mathematically that have been demonstrated, at least theoretically, to be solvable more efficiently with quantum computing resources. And those things include, you know, a prime factorization algorithm called Shor's algorithm that can help to break crypto. Quantum chemistry, which is simulation, optimization, and so forth. And that medium blue center circle certainly isn't drawn to scale. So really the range of problems that can be solved with quantum computing, with the quantum computing algorithms that have been invented to date that have provable end-to-end speed up is really quite small. And then that green area within that medium blue thing, that's the problem type that can be solved by not these universal quantum computers that are being built by Rigetti, IBM, and Google, but rather there's one commercial project, well, 1.5 maybe, but one that doesn't use gate model quantum computing to solve problems, but rather another protocol called quantum annealing to solve problems, and that's D-Wave. D-Wave's kind of well known because they've been around so long, and they were kind of a pioneer in building these processors based on a more rudimentary kind of processor technology. Anyway, we work with both gate model and annealing quantum computers. And to put very simply, the best quantum computers today that are exposed you can still solve larger problems faster on a MacBook Air than you can on a quantum computer, but that doesn't daunt everyone in the technology community that cares about this resource. They understand that in the course of time, quantum processors will become more powerful, and at some point they'll intercept the power you've got for certain problems in classical compute resources. But generally for our company, we look at the types of problems enterprises have that can be addressed with quantum computing resources, so algorithms and hardware, and this is kind of the range of them. So what our company actually does, we actually already we generate revenues, and the revenues we generate are not product revenues necessarily, but we do application prototyping for Fortune 100 companies, Fortune 200 companies, companies that have long product life cycles and have R&D budgets, because that's really what these projects are for companies. So as one or two of the panelists mentioned, none of this hardware is ready for prime time, but there are early adopters in the enterprise community, some of them in the Valley now, that are taking small calculated bets on working on developing applications in-house with the help of companies like ours to figure out, hey, here's a problem we have. It's a computing bottleneck. How can we possibly shorten the compute time of this problem by running it on a quantum computer? So what we do is develop so-called quantum representations or mappings of that enterprise problem into a formulation that's runnable or executable on a quantum algorithm on quantum computing hardware. And we're fortunate to have partnerships with Rigetti, for instance, where we do some of this prototyping, and some of the other hardware vendors. So just very quickly, these are sort of some of the problems we're looking at with enterprises in optimization, in simulation, which is not just chemistry simulation, but there are other types of simulation that occur in the real world, like Monte Carlo simulation, that have broad applicability across industries. And machine learning, we won't get into all the details of what we're doing there. But if we take a step back and look more broadly at what's happening in commercial quantum computing hardware development. So at the moment, at last count, there are 23 commercially funded quantum computing programs. So these range from large-scale technology heavyweights that are building quantum computers to more nimble and very focused earlier stage companies like Rigetti, which has a very particular architecture that they're advancing quickly on. But in any event, there are a lot of companies that are doing that. All of these companies, to an individual, are building off of university research and lab research that's been going on for 20 or 30 years. So all of them are really standing on the shoulders of all the giants in the research community that have been working on this in a very kind of lab, non-scalable or not non-scaled kind of environment. But of course, our bet is that more and more of these technology approaches and projects are going to continue advancing, and companies like ours will have software that runs on those machines. So to get to the point of the speaker from X, it is true that fault-tolerant, error-corrected quantum computers won't be around for some time. But as John Preskill said when he described what should be done in the near term, he said the real challenge is to figure out ways to exploit the limited power of those processors which will be available over the next couple of years. And he coined a term to describe he characterized these near-term quantum computers. They're noisy intermediate scale quantum computers. So this NISQ type of computer, we're in the NISQ era. And so really the challenge for companies like ours is to figure out, it's to be able to squeeze as much power as possible out of those near-term machines. So what we do is we've built a software service platform or a layer that sits on top of the APIs that are exposed by the hardware vendors, and really is doing the translation and mapping of enterprise problems that makes them runnable on these machines, and providing function libraries and domain-specific languages for individual types of problems. So this is kind of a very abbreviated look at what the architecture is. And of course, what we really are as a company is a group of quantum algorithm experts with a little bit of business wrapped around it. Because what I think you really need right now, if you're a software company, is not people that know Python and Java, but it's people that understand very deeply quantum mechanics, linear algebra, quantum algorithms, and the quantum computing formalism. Still at this point, the programming and processing is so complex that you really can't get away with having like a 19-year-old in a garage kind of, you might be able to. I mean, there is that kind of Moneyball person that could do it, but generally you really need people with this very deep formal training in quantum computing to be able to do anything useful with this early stage hardware. So from us, we've managed to recruit some very high profile people from academia who are kind of from the leadership of our quantum computing team. And then we happen to be very lucky because we're based in Palo Alto. And so this is sort of like a welcome beacon to algorithm people that want to work in this field and want to be in Palo Alto. And we can recruit from places like Stanford and Berkeley and Caltech. And so that's quite helpful and convenient to us. We talked about our offices. I did want to reiterate something that Nathan from the group here that organizes kindly pointed out. One thing that our company does try to do is pull the quantum computing and the enterprise community together. So one of the things we thought was missing 2 or 3 years ago in general was a forum that would get the enterprise community, that's going to eventually be the users of this technology, together with the quantum computing community that's building the algorithms and the hardware. So we set up, last year was the first time we held a Q2B conference, so Quantum for Business. It's practical quantum computing. Last year we held it at Ames Research Center at NASA for 3 days. We're doing it again this year at the Computer History Museum, and it's from December 10th to the 12th. Registration is open, so if you would like to explore this topic more deeply, you're welcome to attend. The keynotes are John Preskill and Scott Aronson, both of whom are kind of like TED Talk personalities, but very deeply scientific individuals as well that are kind of considered some of the anchors or godfathers or god people of quantum computing. And the conference is sponsored by all of the hardware heavyweights, including Rigetti, once again, just to plug Rigetti. That's really all I had to say. Are there any questions?
We have time for one quick question.
Yeah, one.
So, since there's a talk about different types of architecture and computing world and mentioned workflow and do you think the existing programming paradigm, like the functional paradigm and paradigm, in quantum computing, would there be a new programming paradigm or a mix of this?
Yes, I think there will. And actually, I think the better person to answer that might be Isaac, because that's kind of one of his focuses. Why don't you take that, actually?
I mean, because it's a factual question, right? It's very factual.
Well, I wasn't really expecting to be in this position, but it's hard to imagine that there will not be anything. But then again, it's not clear what the change will look like in the future at the moment. I'm sorry, but this is all I can say at the moment. So we have a Peril from PsyQuantum.
Well, thank you to the organizers for inviting me here. It's great to see such an amazing turnout. I'd like to start by thanking Stefan for pointing out how hard he thinks quantum computing is. And I totally agree with him. I think building a fully programmable universal quantum computer is going to be extremely hard. So, I just don't want to be recorded. I'm known for saying extremely